Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amir Beruzlan. I'm from Group 3 to present assignment control system. Okay, for the title of our assignment is to controlling system using PID and Ziegler method. By using PID and Ziegler method control, we can control the desirable output of unstable system. Okay, what is PID controller and Ziegler controller? Basically, the pictures show the closed loop system being controlled using PID controller. PID controller is theoretically a controller to give a measurable time to control the common variable, so the system will work in stable condition and give the desirable output. So you can imagine that P is a controller that alter the present error of the system, while I control the past error of the system, and D to control the future error of the system. Okay, in this picture you can see the closed loop system that being controlled and altered using Ziegler-Nicholas rule. It's a heuristic PID controller tuning rule that attempts to produce good volume for the three PID gain parameter Kp, Ti, and Td. Kp is the controller path gain, Ti is the controller of integrated time constant, Td is the controller derivative time constant. Given to measure feedback loop parameter derived from measurement, the period of Tu of the oscillation frequency at the stability limit, the gain margin, Ku for loop stability with goal of achieving good regulation. So it will reject the disturbance. Okay, our group member will continue and show the simulation using MATLAB and see the result.
Assalamualaikum warahmatullahi wabarakatuh. My name Muhammad Hafiz bin Muad. I want to present the method which is Ziegler-Nicholas for P controller. For the P controller, we use coding. Transfer function that we choose is 4 over s squared plus 4s plus 4 for over them second order system. L is time delay and T is time constant that we get from the graph which is graph open loop. Kp is formula of Kp T over L, and control PID Kp00 is P controller, and we run it. Okay. The answer we get is Kp equal to 14, which is P only controller, and the graph we set it characteristic. For characteristic, for the rise time is 0.195. For the peak at 0.414, overshoot is 43.1%, peak amplitude 1.34, setting time is 1.81, last final value 0.933. Okay, we go to second controller, which is Pi. For Pi, we use same transfer function, and just a bit different. We put the formula for Pi controller. And we run it. For the Pi controller, For KI, we get 37.8 and KP is 14. And the result is graph. Okay. For the rise time, 0.165. For the peak amplitude, 1.34. 43.1, 0.414. Setting time, 1.81. And last final value is 0.933. That's all. Thank you.
Alright, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Safi Humaydi Mamazani. My part is result and discussion. Alright. Firstly, for transient function, we have choose 4 over s square plus 4s plus 4. So, for the MATLAB, we put transfer function and we show in the MATLAB. We put s transfer function and we put our transfer function. So, I will run. This is our result, our transfer function, and for figure like this. Alright. Next, to determine the time delay and our time constant, we need to create a tangent and a straight line. So for this, we get the L, we get 0.1 and here, and for the time constant, we get after we calculate 1.5 minus L. So I will show. Alright, this is our PID controller. This is our result. Okay, so we get from our result PID Ziegler. So our transformation, and we get the time constant 1.4. So okay, for the formula, we get Kp plus Ki times 1 over S plus Kd S. So we get Kp 16.8, Ki 84, and Kd 0.84. So this is PID controller. Alright, thank you.
Semiconductor. My name is Iliami Shakira binti Sakara, metric number CE200007. So I will continue with PID controller using PID tuner in Simulink. This is our block diagram that we construct. Our transfer function is 4 over s squared plus 4s plus 4. Click on a step. Our step time is 1, initial value is 0, final value is 1, and the sample time is 0. Click on the PID controller, change to P controller, and P value is 1. Click on tune. Okay, from here we can see the rest point. The block, this is the block rest point, and this is the tune rest point. Click on parameter. We can see the block is 1 to 4.0018. This is the block and tune value. Rise time for the tune is 0.345 seconds. Settling time is 1.87 seconds. Overshoot is 20.8%. Close. Update the block. Click on run. click on the scope and we can see the output waveform for the transfer function. From here, we can see the steady state error. I will pass to my friend for PI controller. Thank you.
Assalamualaikum. My name is Alif Fazhan bin Abdul Rahman. Okay, my matrix number is CE200182. Okay, for the PID auto tune, I've been assigned to do for PI. So, so this is our block diagram that we construct. So, we need to change here for the mat operation to the minus, plus minus. Click apply and OK. And for the PID controller, we change to the PI. And I use the value for proportional. I use for 2, and integral I use 7, and I click apply. I okay. I not tune first. I change my transfer function. So this is our transfer function for numerator coefficient. We use 4, and 4, 4 apply, and okay. So we increase the size so we can see the value. We okay. Then we click for PI controller that we change. We click tune and we wait until he running. Sorry, my laptop got hang when use MATLAB, so we need to wait. Okay, decompile, and it will show the graph. No, wait. Okay, for the Rubik, sorry, it takes a long time to tune, so we need to wait. Oh yeah, come out. We wait for the graph. Why not? Oh yes, come out. So we can see this is the our graph. So we click show parameter so we can show the difference of the blocks response and tune response. Where for the block we use 2 and 7, and after tune it gets for 1.9152, and for I 2.021, and for the rest time for block 0.409 seconds, and tune where the value we get for rest time is 0.651, which one is the rest time is increased. And for the settling time for the block we get 0.66 seconds, and after tunes with 2.96 seconds, and overshoots 56.6 for block response, and for overshoot auto tune we get 6.99. So, and the closed loop is stable both, and we update the block. Wait, start, close. Okay, I will show you the I will, sh- I will show you the output waveform that we get. Oh, we need to click run first. Oh, it's so hard because my laptop quite hang when using MATLAB. Okay, for the scope, we get the graph. As you can see the graph, and the steady state error is eliminated at the end. So which one is good? So you can see. So this is the output waveform. So that's all from me.
So next I will continue with a PID controller. The step is same and the transfer function is same. Click on PID controller, change to PID controller, and the value of PID is 100 and delta coefficient n is 100. Click on tune. From here we can see the response. This is the block response and the tune response. Click on parameter. The block is 1. After the tune, it will become 2.0337. 0, it will become 2.8406. And 0, it will become 0.32616. The n is 100, it will become 243.7041. And we can see the performance from 0.76 second after the tune, it will become 0.368. 2.11, it will become 2.33 for the setting time, and for the overshoot from 4.32%, it becomes 6.38%. Click on update block. Click on run. Click the scope. We can see the output waveform for our transfer function. From here, we can see there is no steady state error. That's all from us. Thank you.
Okay, for the conclusion, from this project we got many knowledge after finish it. First, we learn to determine the effect of the PID controller to the closed loop system, the process of determining the values of a PID controller, proportional, integral, and derivative gains to achieve desired performance and meet design constraints is known as PID tuning. The finding of PI, and PID controller obtained by Ziegler-Nichols are identical to the result of the PID controller obtained from the tuner. According to the experiment, automatic PID tuning is a tool in the PID tuner that allow you to choose optimal PID gains without having to go through the trial and error approach outlined above. We can see we can access the tuning method directly using PID tuner through a pleasant graphical using user interface. Using PID tuner with the automatic PID tuning and the automatic tuning algorithm determine and PID gains to balance performance. As a result, the optimal technique for the control system is automatic PID tuning. Quarter amplitude damping was chosen by Ziegler and Nichols as the optimal control loop response. Although the result lies somewhere between a dead controller and an unstable control loop, we should keep in mind that quarter amplitude damping causes the process to overshoot its sets point and oscillate about it a few times before finally setting down. So that's all for our video. Thank you.